Hi everyone. Um, Now we are going to talk about the differential equations, like ordinary differential equations and partial differential equations in this chapter. This is chapter 25 of Numerical Methods for Engineers. So, in many cases, we have to deal with differential equations for engineering problems like if we have to deal with the flow of some liquids like an air dynamics and some structural problems, some blood flow problems for biomedical. So in most of the cases we have many parameters, and to deal with all those parameters we need some numerical techniques, because the equations are sometimes having more than one variables, and the parameters are huge in number, and the actual solutions or the mathematical solutions are very complicated. So in that case we go for numerical solutions. So in this chapter we are going to talk about how we can solve differential equations using numerical techniques. Okay, so uh, as you know that this equation dv over dt is equal to g minus c over m into v, this equation shows a physical phenomena in which a parachuter has jumped from a balloon and it's going down with a constant velocity. So let's talk about different types of differential equations. There are two main types of differential equations. Number one, ordinary differential equation and a partial differential equation. An ordinary differential equation is that equation that has only one unknown, or only one variable, not unknown, in fact the one dependent variable, that is known as ordinary differential equation. And if an equation deals with more than one, like two or more independent variables, then it is known as partial differential equation. Okay, so and then we have like first order differential equations, second order differential equations, and even more higher order differential equations. For example, this is one pendulum, it's moving, oscillating. We can make equation, we can convert this physical phenomena into mathematical model. The same thing is about the parachuter. We have a physical law, then we write ordinary differential equation, and then we solve it. And in order to solve, we have two ways. One are the analytical ways using mathematics and calculus, and the other ones are numerical ways by which you can use numerical techniques, different methods, in order to solve these equations. So let's move to the next chapter, chapter 25. And in this chapter we are going to deal with the ordinary differential equations, and these methods are based on Runga Kutta's methods. And the first method in the methods proposed by Runga is the first method is Euler's method. So this method is very simple. In this method, for example, if there is y is the function on y-axis, for example, y is like the unknown dependent parameter that we have to explore, or after integration what the function itself that we need is y, and x is the independent variable. So for example, this is the y. So in the initial point or the initial conditions, at this point we have xi and yi. So in order to use the Euler's method, you should have the initial conditions. For example, what is the value of yi or y when xi is like started? For example, these are known as initial conditions, the start of the function. So in that case, if we have the initial value of xi and yi, then we can move next. So how we can find the next value? We can say that the slope at this point xi and yi is known to us, and if we just find the slope at this point and we multiply with the interval, so we and add into x yi, we will get the next point. So what is this method? I explain you once more. For example, you have the slope of this line, okay, and you have the interval h, and you have the initial value yi. So it means that if you multiply the slope with this interval h, you will get this height, and if you add this height into the initial value yi, you will get the new value yi plus 1, and that value will be at xi plus 1. So this is how all this method works. It's very simple, very easy, and we can solve some problem. For example, this is the equation. How we can get the next value of y, which is actually the integration of the ordinary differential equation. So we have the previous value yi plus this is the slope. This is the slope, the same thing slope, or this is also equal to dy over dx at xi and at yi multiplied by intervals. So if we have the derivative that we have to solve, in fact, because we will be having this derivative, we want to convert this derivative into the original function. So we want to integrate it, in fact. So we have this function, this derivative we have, so we will put xi yi, we will get the slope, we will multiply with the interval, and then whatever we will get, so we will add into the initial value, we will get the next value. So this is how all this method works. So let's solve one example. This is the Euler's method description. This is the slope that I just explained to you. This is the same equation 25.2. So let's solve this example 25.1. We have this function dy over dx. This is the function, the integration or the ordinary differential equations that is there. So we have to solve, or we have to integrate in order to get this y. So it means that we have fxi or yi. This is fxy, or this is phi, or this is slope. So we have this equation, and then this is the initial conditions. For example, at x is equal to 0, we have to move from x is equal to 0 to x is equal to 4 with the step size or with the interval of 0.5, and these are the initial conditions, the values from to start with. Xi is 0, yi is 1, and then this is the true value of the function. Actually it is given in this question because if we have to find the true error, so we should have the true value of y, so we can compare the values from this equation, and we can also compare the values in this equation, so that we can solve and we can see what is the amount of true error. So that is why in this question we have been given with the true solution, or with the analytical solution, or the exact solution as well. Okay. So let's solve this equation. Let me put this over here. I put it here in Excel. So we have this Euler's equation here. Okay, and then let me take this one as well. Okay, so let's crop it. So now we have we have the slope, we have the function itself, and we have the interval 0.5, the initial conditions, and from where to start and where to end. So okay, so if I say this is f xi yi, okay, so I can start with, for example, xi. I can make a column. This is xi. Xi is 0. The initial value is 0, and then 0.5, then 1, and we can go up to 4. So let me increase the size for this. Okay, 0, 0.5, 1, and then okay, so this is xi, and then what will be the slope? Fxi yi. For example, the initial value of yi is also given here, but we don't need in this equation the initial value of yi. So sorry. Okay, actually I want to reduce this size. Okay, Okay, so now we can find the slope at each value of xi. We have the interval here. Okay, for example, the interval will be 0.5 for all these cases. Okay, and then how I can find the fxi yi, the slope at each point, for example, minus 2 into xi cube plus 12 multiplied by x square minus 20 multiplied by x plus 8.5. So this is the slope at this point, and then we can have the slope at all these points, the next points, and then how we can find the yi plus 1 yi plus 1 is simply, for example, we have the yi. For example, when x is 0, the y here, for example, the y is 1, it is already given here 1. So what is the equation? The equation is yi is 1 plus or for example, if you want to make it more prominent, we can add one more column here like yi and control x, control v. Okay, let's say this is yi. For example, when you have the xi, the yi is given, that is 1. Okay, and then how you can get yi plus 1? Yi plus slope multiplied by 0.5 multiplied by interval. You can say 0.5, or so this is actually 5.25, and now in this case yi will be this value. Okay, and then we can do the same control C, control V here. I think I'm doing some mistake. Let me see what is that. So okay, so this is slope. So now the slope will be minus 2 minus 2 into okay, plus 12 plus 20. Actually this is not 20, this is actually minus 20x. Okay, so also let me correct here, this is minus 20. So let me check once again, minus 2 into x cube, okay, plus 12 to x square minus 20 into x plus 8.5. It seems correct. Okay, so control C, control V here. Okay, I believe that these values are correct, and this is the yi plus 1, and this is the same thing. So just control C and control V. You will keep on getting the values of y. And now how you can get the yi plus 1 true value? True. This because you have this function here. So if you just put x, for example, x, when x is 0, yi is actually given. So let's do it for the next step. For example, when minus 0.5 into x 4 x raised to the power 4 plus 4 into x cube minus 10 into x square plus 8.5 into x plus 1. So let me check again. Minus 0.5. Okay, so minus 0.5 into I20, okay, plus 4 into, okay, plus 10. It's not plus 10, it's actually minus 10, plus 8.5. Okay, so this is 3.215, and you can find out the true error. For example, in this case, because you have the yi is for example, if you want to compare, now this is actually yi and this is the yi. You can say that yi, I should write here yi true, because okay, so this is actually the value that you are getting at x is equal to 0.5, 5.25, and because this is yi plus 1, this is not for xi, this value is for xi plus 1. So this is actually xi plus 1, and this is the corresponding value of yi. So we have to find the true value based upon this xi. So we should compare yi with this yi true. Okay, and then you can just find the true percentage error. For example, true value minus approximate value divided by true value divided by 100. So this is 63.1. Control C, and if you do Control V, you will get you will get the value of yi. For example, here we have the value of yi already, so yi true value, if you just Control C and Control V, you should get 1. So in that case it should be 0. Okay, so this is how we can solve, we can find out, but in that case you can see there's a huge difference between the true value and the numerical values. So if you want to plot, you can also plot. For example, if you want to make a plot, let's make a plot here. Okay, and then let me remove all these series. Let me add one new series. For example, okay, say this is x, and then this is y true. Okay, this is the first series, and then we should have the other series 2. Okay, this is the x, and this is the y numerical. For example, you can say this is the y numerical. Okay, so you can see there's a huge difference between these two values, and let's compare our values with the book values. So almost we are getting the similar trend of the charts. Okay, and then these are the book values. So if you want to compare, we can compare our values. For example, here this is the xi yi Euler value. So this is 1, 5.25, 5. Okay, it seems the pretty same values. And this is the global error, the true error, which we can see it here. So in all these cases, so this is how we can find out the solution. So if you want to make your solution more accurate, so what you can do, you can reduce the interval. For example, let's see what happens if I reduce the interval from 0.5 to, let's say, 0.25. For example, this is 0, this is 0.5, sorry, 0.25 plus this value. Control C, and then Control V. Okay, and now the interval is 0.25